All right, so let's start with number 25. Okay, that showed up quite a bit on the poll there. They tell you that h of 0 equals 0, and they tell you that h prime of x is less than or equal to -2. Now, some people were thrown off by the Roman numerals there, the I and the double I. That's just Roman numeral 1, Roman numeral 2. All they were telling you there is, hey, here's two pieces of information. Okay, so that's all that was about, notation. All right, and so they tell you this, and then they ask you a question about h of 5. They said, show that h of 5 is less than or equal to -10. Okay, now several people that I've helped with this, I've said, well, the first thing you should do is draw an H graph. And most of them looked at me like I was nuts. Like, what do you mean, draw an H graph? What do I mean by draw an H graph here? Draw a graph that has H as its y-axis and the point 0, 0. That's right. H of 0 equals 0 just tells you here's a point. The function is H, so that's its outputs, the y values, right? The outputs are H, and the inputs are X, and that's 0, 0. So that's what I mean by drawing H graph. Start there. Okay, then they ask you about H of 5, which means when you have an input of 5, right, when the X is 5, they're asking you something about that. Okay, then what does this say? Slope. H prime means derivative, which we said means slope or rate of change. For us right now, we'll talk slope. Go ahead, Brittany. Slope. Less than or equal to -2. Now, when I read less than or equal to -2, what helps me is to write numbers that are less than or equal to -2. So when I read that, I think, okay, so the slopes are -2, or maybe -3, or maybe -4, -5. Now, what's that mean if slope's negative? Goes down. So the H graph, so we know the H graph has to go down. And not only does it have to go down, but think slope is rise over run. It's got to go down for every one it goes over, it's got to go down 2, or maybe 3, or maybe 4, right? It's got to go down 2 or more. So what about H of 5? Well, that means if it goes over 5, it's got to do what? It's got to go down 10. That's what that says right there. The slope is less than or equal to -2. So it's -2, -3, and 4, something like that. Well, so therefore, the output at 5 has to be -10 or lower. -11, -12, -13 has to be less than or equal to -10. So that's how you answer part A. A picture with a sentence or two would describe that. Okay? Now, they tried to fool you then a little bit by doing the next one. H of 3 has got to be less than 5. How would you explain that? Same way. Same way. You would say, well, if you're going to go over 3, what do you got to do? You got to go down 6, at least, maybe farther. So H of 3 has got to be less than or equal to -6. Now that confused some people, thought, well, they put a 5 there. Well, if it's less than or equal to -6, it's certainly less than 5.
They put less than and equal to 5.
But it's or, right? It's got, isn't it true that H of 3 has to be less than or equal to 5? Now you're right, it'll never be 5, but that's okay, right? Remember computer math, and or, just one or the other has got to be true, right? And so H of 3 is always going to be less than 5. It's also going to be less than or equal to 5, right? Because an or, if just one of those is true, then the statement is true. So that's it. But again, they tried to trick you by putting a 5 there instead of a -6, which you were expecting, which would have been like this one. All right. It's kind of like saying, right now in my pocket, I've got less than or equal to $1 million. That's a true statement. Okay? That's a true statement. Okay? And to be a true statement, I don't have to have $1 million. Okay, it doesn't have to be. All right. So then it says in C, use card talk. Now this, I think you're going to see in this problem, and also number 35. Because many of you had pictures for 35. Some of you only had one picture, not 3 pictures. But I think you're going to find out 35 that there's a lot more going on in problem 35 than you may have thought. And this is what the point I'm making, and the same thing here with 25C. Some of you may not have had a question about 25. You may have looked at the back, or maybe you got some kind of look back. Yeah, that's right. But did you really understand? You know, not on a superficial level, you know, but do you really understand all the different facets of what's going on there? And that's what you want to really try to get to. That should be your goal. So this one says in car talk. Okay, so let's use car talk. The Bismarck, the car moving around. So now H, I'm going to put units on my y-axis. What would be my units for H here? Miles. Okay? And this would be hours. And what would be the units of H prime? Miles per hour, because we said H prime is slope. And remember, whenever you do slope, it's y's on top of x's. So that means the slope, H prime, would be these units, the y units, over the x units. So it's miles per hour. Okay, so what does H of 0 equals 0 mean in car talk? We start at Bismarck, the origin. So at 0 times 0 at noon, we're going to be in Bismarck. That's what that means. What's this mean?
We're going to go south of Bismarck.
We're doing east and west.
Okay, east.
Negative is west, right? This is speed, or velocity, excuse me. Negative means west, 2 mile an hour. So we're going to be traveling west at 2 mile an hour, or, now you got to be careful, it says less than or equal to, but speed-wise it would be, that's where these numbers come in. I'm going to be going 2 mile an hour west, or maybe 3 mile an hour west, or maybe 4 mile an hour west, right? Because it says less than or equal to -2. So would it be faster? Right? The word here should be faster, right? We want to be careful saying less, because that's not that meaningful with velocity. Okay? -2, -3, yeah, my velocity is getting less, but that doesn't really tell us what's happening. We're getting faster. It's negative though, because it's going in the other direction. Okay? That's what I was saying yesterday. I think I said this yesterday. You can't, just because the velocity is negative or increasing or decreasing doesn't mean you're going faster or slower. If I tell you my speed is increasing, yeah, I'm going faster. But if my velocity is increasing, that doesn't necessarily mean I'm going faster, because it has direction, okay? So that's important. All right, so we're going 2 or 3 or 4 or 5 miles an hour to the west. So what's this saying then? We're supposed to do parts A and B in car talk.
By 5 hours.
By 5 hours later, 5 o'clock,
I must eat.
at least 10 miles west. Well, that makes sense. If I start here at noon, H of 5 is less than or equal to -10. If I'm going at least 2 miles an hour to the west, then in 5 hours I have to be at least 10 miles west. Okay, what about this one? This one's a little trickier. 3 hours later, at 3 o'clock,
I have to be at least 5 miles east of Bismarck.
well, 5 is, as a position, 5 is over here. It's positive, right? 5 is east of Bismarck. But what does less than mean? West. I have to be west of 5 miles east. But aren't I? Because what am I doing? I'm starting at Bismarck and I'm going 2 miles an hour to the west. So 3 hours later, I have to be west of 5 miles east. Well, absolutely. As a matter of fact, I'm going to be where? I'm going to be west of 6 miles west, right? I've got to go in 3 hours, I've got to go at least 6 miles west and possibly farther. So I'll definitely be west of 5 miles east. Take a break after that one. All right, but that's how we want to say it. And again, it's looking at this H prime business as a slope, mathematically as a slope in one way, or thinking of it as a rate of change if we have units on it. All right, let's go over to 32 and 35. Okay, number 32 here. All right, on page 32, or excuse me, number 32, we say that we want a position graph, a velocity graph, and it could be negative, and we want an acceleration graph. Okay, now, what's another name for the v function? P prime. And another name for the acceleration graph, V prime or P double prime. Okay? Now remember, what the prime means is it means derivative or slopes. So P double prime would be the slopes of P prime. P prime are the slopes of P. Okay? Or V prime is the slopes of V. Same thing as P double prime is the slopes of P prime. Now, I can't emphasize this enough, and over the next 3 or 4 days, this is going to be crucial for you to understand that this graph here, the P prime graph, its Y values are what compared to this? The slopes. These Y values, these outputs, are the slopes of this graph. And these Y values are the slopes of this graph. So each graph has a couple things going on. It's got its Y values, its outputs, but it's also got slopes. Okay? And so we've really got to keep those two things straight. So on 32, they say, this one's a little easier. This one says, the object moves away from the origin at a constant velocity. So we know it starts at the origin, and it's got a constant velocity. So what am I going to draw? A straight line. Well, yeah, a line. There is no, in math, there is no such thing as a crooked line, okay? And all lines are straight. If it's not, it's curved, okay? So, but I say straight line sometimes too. It's a line, and it'd have to be in a diagonal, right? It's got to be going away from the origin, okay? Now, how steep it goes up is up to you. They don't really say. But since it's a constant velocity, it has to have a, it's got to be in a line. All right, so what would then the velocity be? Horizontal line. Where?
Anywhere.
Can't be anywhere.
Not on the.
It's the slope of this line. So if this line has a slope of 3, then where's this got to be? A horizontal line up here at 3. Okay, but it's got to be positive. It can't be anywhere. It couldn't be down in the negative, I guess is what I'm saying. It can't be below the x-axis. It's got to be above the x-axis because this is a but these are constant. This is a slope of 3 all the time, so this should have a y value of 3 all the time. What's it going to be over here? Horizontal line at 0, because the slope of this is 0. Well, of course, if you have a constant velocity, you have no acceleration, so the acceleration should be 0. Okay, so that part wasn't too bad. All right, now let's go to 35. 35 says the object moves to the right and then it moves to the left. Where do I start it? Does it have to start at the origin? Doesn't say, does it? Now you could start the origin, be fine, but it doesn't say. So there's all kinds of options here for you could draw this. But let's go ahead and start at the origin, even though it didn't say to. Now it moves to the right. So could I just draw it as a line? How many people drew it as a line? Okay. Now when it goes back to the left, goes back down. Now does it have to go all the way back to where it started? Didn't say it did, but we could. That'd be fine. So this would be one possibility right here. Okay. But there are other possibilities. Couldn't this thing have done this? Right? Wouldn't that be the same thing? Went to the right, then went to the left. Now what would be the difference between those two? If I was actually doing it right here, if I was actually walking. The velocity. So let's do the black one first. What would I have to do to do the black one?
Constant velocity.
Constant velocity, right? Including right from the start. So I'd have to already be moving, right? When I got to 0, I'd have to already be moving, right? Because there's got to be some acceleration time to get up to speed, right? So I'd have to already be moving. So once I hit 0 and I just stay at a constant velocity, what happens when I get to the tip of the triangle? Do I stop?
No.
If you draw it as a triangle, you would have to instantly go from whatever, 5 miles an hour, whatever your velocity was, to negative 5 miles an hour, right? Instantly. In a physical situation, this would be really hard to do, the black one, right? Now, you're going to find out that we're going to say that at this point, at this sharp point in the graph, the slope is undefined there. There is no slope. There isn't a slope of 0. The velocity never becomes 0 right here. When you do that sudden change of direction, it has to be instantaneous. You have to instantly go from 5 mile an hour this way to negative 5 mile an hour the other way, which I think pretty much impossible physically. There'd have to be some slowdown and some start back up. And that's what this curve would represent. This would be starting at a certain speed and then slowing down until here, and then turning around and then gradually picking up speed again. So the blue one would probably be the more realistic of scenarios. Now we could do this. We could start at a stop and speed up, gradually speed up, right? And then instantly go back and then slow down. I mean, there would be all kinds of possibilities of how I could draw it, going to the right and going to the left. Basically, it's got to do what? Go up and then go down, right? If you drew something that went up and then went down, you're good. You described the situation, even though it might not be physically possible. But I just want to look at all three of those because I want to show you how that affects this. See, that's the real key to this problem, is how does this graph affect this? Let's take the black one first. What's this going to look like for the black one? What kind of line? A horizontal line, right? Not a diagonal. It'd have to be horizontal. Because it's just like the first one we just did. It would have a constant positive slope, and then what at the point? Instantly switch to a constant negative slope. It would be that, wouldn't it? Right? So if you drew the black one as your position graph, then you have to have this for your velocity graph. Right? And then what would be the acceleration graph for that? Horizontal line at 0. Because, now again, come back to slopes. The slope of this might be 3, and the slope of this side might be negative 3. So what I graphed here is 3, and then I graphed negative 3. But the slopes of these are 0. So the slopes of this are the y values I plot over here. So you'd have just a line right at the axis, 0. Okay? Let's do the blue one. Where would I start the blue graph? The blue derivative graph, slope graph, velocity graph. The way I drew it up there. I could not start it at 0, could I? Because here's what we want to look at. And again, I'll say it again, what I'm trying to draw right now, I'm trying to draw y values that are these slopes. So what's helpful sometimes is to go on a graph like this and draw little tangent lines in there. Draw little tangent lines, those are the slopes. Now this slope looks to me like it starts out positive and pretty steep. But then it goes, and it's getting less steeper, isn't it? Isn't that kind of what the blue slopes are doing? They're starting at like a 5, then a 4, then a 3, then a 2, right? So I better start up here somewhere and go where? Down. And right here at this peak, my slope is 0. Then what are the slopes doing? Negative and getting, this is a phrase you'll hear me say quite a bit. The slopes here are positive but getting less positive, right? 5 slope, 4 slope, 3 slope, 2 slope, right? They're positive slopes and getting less positive, and then they become negative and get more negative. I don't know if that's even a correct term, but I think it makes sense. -1, -2, -3, because technically that's decreasing, isn't it? Isn't -1 to -2 to -3 decreasing? Right? See, I always think of it this way because we're going to use the term increasing and decreasing a lot, and it can get confusing. So I think to help that, if you think of it this way, these are two different ways for numbers to decrease. They're either positive and get less positive, or they're negative and get more negative, right? Those are the two ways that you can decrease. Well, if I want to graph negative and get more negative, it would go down like this. Well, clearly that line is decreasing. right? Up here, it's positive y values and getting less positive, and down here it's negative y values and getting more negative, but that's decreasing. That's also something we'll talk about next week. That's why the blue graph is concave down. When its slopes decrease, the graph is concave down. But there's two ways to be concave down. It can either be going up like this, positive slopes getting less positive, or it could be going down like this, negative slopes getting more negative. Okay, but that's for another day. Now, I would ask you this. If my first graph was this curved blue one, is this how my second graph would have to look? Would it have to be a line? What do you think? Why it says it could be curved. What does that, if this is my blue position graph, what would this graph, this blue graph, have to do? Well, no, I think you're thinking backwards. If this one is this, then what's this do? I'm just saying, when I drew this blue graph, you guys all told me you started up here, right? And it was doing this. What did this blue graph have to do? Go down. The blue graph had to decrease. It had to go down. But did it have to go down in a straight line? See, there I said. Did it have to go down in a line? No. It could have curved, but it had to decrease. See, if it goes in a line, and that, Jacob, I think is what you're saying. If this curved at a constant, if these curves were changing at a constant, -5 to -4 to -3, then yes, this would be a line. But it wouldn't have had to be. Okay? Wouldn't have had to be. See, that's important. So there's a lot of stuff going on here. We haven't even gotten over to the red one yet, or even to this. What would this be then? If this then is we said it wouldn't have had to be this, but if this was my velocity graph, my P prime, what's P double prime? It slopes. Horizontal, where? What's this slope right here? -7? It's negative, right? So wouldn't it have to be down here? It'd have to be a horizontal line down in the negative. But it'd have to be horizontal. If this was a line, then this has to be a horizontal line. Because this graph is the slope of this graph. And this slope is constant, since I drew it as a line. Now, if this slope, if I would have drawn this as a curve, but it was going down all the time, then I'd have had to make sure this was just negative. But it could have been curved as well. Okay? Man, it hurts. This is the second time I've done this. All right. Let's do the red one. What would change? What would my slopes be doing on the red one here at the beginning? Or what would the slopes be at the beginning? Small positive, right? Maybe even starting at 0. And then getting what? More positive. So how does I graph that as a y value? Positive and getting more positive. Got to go up. And we'll just assume it's going up constant, so we'll just make it go up. Until there. Right? And then what happens here? Those are negative slopes and getting... Which? I heard more, I heard less. Isn't this a slope of like -5, -4, -3, -2? We're getting less negative. Right? -5, -4. So how do I graph that? It's got to start down here and go like that. Look how different those curves are. Right? So there's a huge difference. And then what would be the red graph over here? Because these are negative y values but getting less negative. What would these slopes be, the red slopes be over here then? Just be a horizontal line positive, wouldn't it? Assuming that these were parallel, assuming these had the same slope. What a difference. I mean, so in that one little problem, goes to the right and it goes to the left. We can have all these different variations off of that, depending on the rate that it goes to the right and goes to the left. All right, on 37, it just says moving towards the origin at steadily increasing speed. So now, if he moves towards the origin at a... Oh, shoot. Sorry, whoever I'm recording this for. The screensaver came on, so now in the recording of the movie, they'll have the screen. They'll have the screens. They'll hear my voice and get a look at the fish. All right. So Hopefully it wasn't on too long. That's for, well, that's for, who's that? That's for Anna. Sorry, Anna.
Fish.
All right. See, now we'll see if she really watched it, because then we can ask her. We can ask her if she saw it. Did you see the fish? All right. Moving towards the origin at a steadily decreasing. No, wait, that's the wrong one. Moving towards the origin at a steadily increasing speed. So it's got to start up here and go.
Get steeper.
It's going towards the origin. So where's it got to go? Down and get steeper, like that. We really have no choice here. It's pretty much got to do that. And it's got a curve. It can't be a line. Because it says it's a steadily increasing speed. So it's going faster and faster. So it's got to get steeper and steeper. So then since it's steadily decreasing, now we got slopes that start out like almost 0 and then go more negative, right? So if they start out at 0 and go more negative, wouldn't it have to be a line down here? You really don't have much choice on this one. It's pretty much got to look like that. You got negative slopes and they're getting more negative, so your y value's got to get more negative. And then what would happen over here? Horizontal down there in the negative. All right, the key thing to take away from this, though, is being able to look at the slopes of one graph and plot it as y values on another graph. Okay. That wasn't the fish. That was the salmon. All right. So now, what else did we have? 41 was one. 47. I want to talk about 47. We'll come back to 41. 47 says, write the equation of the tangent line of the graph of f. Now, when you hear the words, write the equation of a line, what should you do?
Set up your function.
Point slope form right away. Here I've been warning you about this since we did Appendix C. This is when it comes into play right here. Find the equation of the tangent line to f. Now, to do that, we need a point. We need a slope. Now that we're into the function notation, and now we got this new thing for slope called the derivative, the next thing you should write down is, okay, I need a point. They tell me f of 1 is my point. You should write this, just like you should just get in the habit of doing this. If you get in this habit, these equation of tangent line problems will be a piece of cake. Because what did I just say? What's this? This is my point, and this is my slope. There you go, because that's what f prime is. So, luckily, they told me f of 1 is 5. That was nice of them. They don't always do that. Sometimes we have to find it ourselves. And now we have to find the slope of the f graph at 1. Now, this will come in a variety of different scenarios. One scenario, and you'll have to do this on your homework quite a bit today, is if I give you the f graph, and that's a terrible f graph for what I had in mind. Try that again. If I give you an f graph that looked like this, and here is 1, one way to find that slope would be to what? Draw a tangent line. Now, if I told you the equation of that, then we could plug in 2 points really close together, calculate a slope, right? Zoom in, like we talked in Appendix A. That's a big part of actually what Section 1.5 is that we'll be doing today. But a lot of times you get a graph where they don't tell you the equation, and they ask you to estimate the slope. So what you'll do is you'll come in here, you actually do this on the test. You probably looked in your book. People from before you have already written in there, haven't they? They've already been drawing tangent lines, and then you can just use what they did. But I asked them to erase it, but oh. So, but you just draw yourself a tangent line, and then just do a slope triangle. Do a rise over run thing, right? That might be the best you can do, is estimate what the slope is. If you don't know any more than just a picture, and you want to do the slope at 1, draw in a tangent line, do a rise over run. But they were nicer to us than that. What did they give us? They gave us the actual f prime graph. That means we're going to look at what on that graph? The y value, right? The y value of the f prime graph is the slope of the f graph, which is what we want. So what's the y value? 2. So all you had to do is look at the f prime graph, look at the y value, it's a 2, there's your slope. So all that's left is for you to plug your 2 there, your 1 there, your 5 there, and you're done. That's all you had to do. Write the equation of the tangent line. Okay? Very important type of problem because we see it all the time. All right. 41, what am I forgetting? 41 I'm going to do. Am I forgetting something else that a lot of people had mentioned there? Was 51 one of them? Huh?
41.
41, it was 41. Okay, 41, let's do 41. 41's a good one too. 41 says, let H represent the time in hours between sunrise and sunset, T days after January 1. Whenever I read a sentence like that, I'll be real honest with you, I usually draw a graph. Even though there's no graph to draw on this, the axis and the units help me. So if I was going to do this problem, I would probably, first thing, I'd put T down here, and I would write hours, and here I would write daylight hours, or just hours, but I'm sorry, I did that wrong. That's not hours down here, is it? It should be days. It's days after January 1. But this is hours. It's a time between sunrise and sunset. That's daylight hours, okay? Call it just hours if you want. So drawing that helps me because what will H prime's units be then? Daylight hours per day. The derivative is always the y's divided by the x's. So it's going to be hours per day. All right. So they said to interpret this, and this will be, again, if you want to make any notes for the quiz, this, something like this, where you have to interpret this in regular language, like that car talk stuff we were doing earlier. Here's a scenario. Interpret this notation into that language. This will be something you'll have to do. Somebody got one they want to share with us? Preferably not the one out of the back of the book.
I put that it was near a maximum or a minimum
Oh, why?
because the slope is almost 0.
Since the slope is almost 0, it's at it must be at a time when there's the most daylight hours. Now 100 days would be when? A little over 3 months, January, February, March, you'd be into April. Okay. Did anybody, 0.05 would be in hours. Did anybody convert that into minutes? How would you convert it into minutes?
Wouldn't the point
Well,
of be
Isn't this hours?
per day?
No. Oh, this, yes. Well, okay. So convert it into minutes per day, I think. Okay.
Wouldn't you just take 0.05 times 60?
0.05 times 60, which is 3. So think of that as 3. So this would be 3 minutes per day. But let's keep going. We really want more than that. I mean, that's not necessarily a bad answer, but I don't think it's the full answer. Okay, what we want to do is interpret just what this is saying. I think what you did is go beyond that to say kind of, what the graph of H would be looking like. But we just want to interpret this.
So 100 days after January 1st, there'll be 3 hours of daylight.
3 minutes.
Or 3 minutes.
There won't be 3,
Well,
well, hopefully there's not 3 minutes a day.
There'll be 3 more minutes.
3 more minutes, okay. Or, okay, that's really interesting that you said that. There'll be 3 more minutes of daylight than,
January 1st.
no, not the January 1st, the day before, the 99th day. On the 100th day after January 1st, there'll be 3 more minutes of daylight than there was the day before. Okay? Now that's interesting that you said it because usually people don't think of it that way. Now that is a good way to talk about it though. Okay? The more common answer there is on the 100th day, the hours of daylight are what? Increasing by 3 minutes per day. Okay, so that'd be a good way to say it. And why is it increasing? Why is there 3 more?
So it's positive.
because it's positive. Since the slope's positive, we know the H graph is going up, and so we would say increasing. If this was negative, we'd say decreasing. There's 3 less minutes of daylight. Now, let's talk about this because it's really kind of a neat application of calculus here. You know, if you watch the weather or whatever, a lot of times they'll give you the sunrise and the sunset time, you know, and so you can calculate how many hours of daylight we have. And right now we're in a period where the days are getting shorter, obviously. You know, coming this weekend, we got daylight savings time ending, and so they really seem to get short. But what are the important days of the year when it comes to daylight hours and so forth? You know what I'm talking about? The solstice and the equinox, right? When are those?
Solstice in summer.
In the fall? What's the one that we just passed in September? The fall or autumnal equinox, right? Now, it's pretty easy to remember the months these happen, okay? They happen in these months here and always right around the 21st of the month, okay? So in March, we have the spring equinox. In June, we have the summer solstice. In September, we just have the fall equinox. And then in December, we'll have the winter solstice. Now, equinox comes from equal because what happens in March and September? Equal number of hours of daylight and nighttime hours. You have exactly 12 hours of daylight and 12 hours of night. Okay? So that's equal. Solstice. What's the word solstice come from? Sol is sun. Solstice comes from when the sun stands still. Okay? Now, let's think about what the sun does in the sky as the seasons change. If we're looking, this is east to west right here. Now, in the summer, the sun is pretty high overhead as it comes across, right? From east to west, it's pretty high in the sky. In the winter, where is it? It's more over here to the south, right? As the sun comes across during the day from east to west, it's more over here to the south. It's much lower in the sky, okay? If you were to draw a picture, it might look something like this, okay? Where this is to the south, this would be straight up above us here, okay? And so this would be like the sun coming at us, right, from east to west. In the summer, the sun's up here, not maybe quite overhead, but almost overhead, right? A little bit south because what? We're north of the equator, is that why that would be, right? It's still a little south of this, but if we were at the equator, it'd be straight overhead? Maybe not. I don't know what that was. But the point is, in the winter, that sun, as it comes across, is pretty much straight overhead. Now in the summer, it's lower, it's down here. Okay? Now I drew that a little bigger because isn't the sun a little closer to us in the winter? It's a little closer to us in the winter than the summer, so I drew it a little bigger. Okay, so anyway, what happens then, in June, when we have the summer solstice, now with every day that goes by, that sun, as it comes over, is a little bit lower in the sky. And the sun, you might say, is on its way to its southernmost point, which happens in December, right? Now what happens as the sun gets all the way to here? What happens then as after December 21st? Starts going back the other way. Well, if I go right, then left, what do I have to do before I go back left? I have to stop. So when you get to the winter solstice, the sun stands still as it then heads back in the sky up to the north. And then in June, it gets to its highest point and stands still. That's where the term solstice comes from. So the winter and summer solstice. Okay? Now, how about the amount of daylight hours per day? Okay? We just said on whatever the 100th day is, we're gaining 3 minutes per day. Is that equal all through the year? Do you gain 3 minutes per day every day? No. I mean, think about it as the days go by. June 21st, the longest day of the year, the most daylight. June 22nd seems like it's still a pretty long day. Matter of fact, late into July, even into August, the days seem pretty long, right? Daylight till almost 9 o'clock. It's changing, it's pretty slow. But as then the fall gets here and it starts moving, Don't you notice that? You get into September, the days seem to get shorter in a big hurry. Well, that's because it's moving on its way here faster and faster. When do you suppose it hits its fastest? When is the daylight hours changing the most rapidly? In September 21st at the equinox, right here in the middle. At what point do you suppose we would call that? The inflection point. That's the inflection point. Because think about a graph with the inflection point. That's the steepest part of the graph. And if we're talking velocity, that's where the sun would be moving the fastest. That's when the days would be getting shorter the fastest. And the same thing in March. That's when the days start lengthening the fastest. Okay? And that would be the inflection point right there. So the equinox is the inflection point between the daylight hours. Okay? So there's kind of some neat calculus connections there. In B it says, for what values of t will h prime be less than 0? Well, that means negative. When will h prime be negative? You probably didn't find the t values exactly, but let's use dates. After when? After what date? June 21st, after the summer solstice, right? Because after the summer solstice, the days are getting shorter. We're losing daylight hours, and so the slope would be negative. Okay, so that's what part B would be about. Okay, let's take a look at section 1.5, if that's all we got then. So I think you might discover there that there are some things that you learned, or some things we discussed that you might not have been thinking about as you were doing the homework, but they're important. All right, let's All right, go ahead and get your calculators out now. All right. Let's graph on your calculator y equals x squared. Okay? Just go in your scratch pad part of your calculator here. And who wants to be presenter? Pass that back to Dan. Who wants to be presenter? Kelly will?
I don't have a graph.
Okay, I'll just pick somebody. Okay, who am I going to pick? Ross. Ross is a presenter. All right. Because I screwed this up last period, so I don't want to do that again. All right. So let's see. Can I make the calculator show up here? Oh, okay, there it is. All right. So why can't I see? Why can't I grow that a little bigger? Okay. There we go. All right. So, what I would like us to do, what the emphasis is today, in section 1.5 is zooming in, okay? And we did that a little bit with that Appendix A. And we also have done some of this, so it isn't that new. We did some of this at first day where we said if you want to do the slope at a point, then you need to get 2 points really close to that point so you can do a slope calculation. So if I was to look at this, let me put this on the screen for my recording, but if I was to ask you, we just graphed f of x equals x squared, and now I'm asking you for f prime of 2. Okay? All right. So, what are the different ways we can find the slope of the x squared parabola at 2. Okay? Well, one would be what we said earlier. I could sketch in a tangent line. I could draw it on my paper, could sketch in a tangent line. I could do a little slope triangle and count rise and run. But since we have an equation, we usually wouldn't do that. Okay? So we could pick 2 points really close together. Now there's 2 ways I want you to be able to do that. One way would be on just the calculator screen. So Ross, go to the calculator screen of the scratch pad. There we go. Okay, just hit the button over there, or go up to there. Everybody go to the calculator side. And now let's just do a slope calculation with 2 points really close to 2. So use your, maybe your fraction. If you hit control divide, give yourself the fraction thing. Okay, that's good. Now we want to subtract the y-values. Now what 2 points really close to 2 should we use? 1.99 and 2.01. Sounds good. So go ahead, but now how do we plug those into that function? I think I showed you this. F1, where we had just put this in already, is in F1. So type F1, F, because we put the equation in. Yeah, just like that. Because we since we graphed it, when we graphed it, we stored it in F1 of X, right? So now you can put F1 parentheses, okay, and it would look like, now what do we put in here? 2.0, let's put 2.01, doesn't matter actually which order we do it. Okay, and then minus, oops, back up. Yeah, no. 0.01. Okay, that's the first y value, right? And then we want to subtract the other y value, so we have to arrow out of the parenthesis. And then minus, there you go, now do the F1. You have to do the F1 again. Okay? Wouldn't that be subtracting the y's right there? And then what would go on the bottom? 2.01. So you just tab down 2.01 minus 1.99. And then hit enter. This would be our slope calculation. There you go. So it tells the slope of 4. Now, does that make sense? Picture the x squared parabola. Does it make sense to have a slope of 4? Seems reasonable. It'd be pretty steep at that point. Okay, so that's one way to zoom in, is to zoom in numerically. In other words, I just picked a couple of numbers close to 2, so I didn't literally zoom in, but I did zoom in numerically. Okay, go back to your graph. Everybody go back to their graph. Now let's do the thing we did yesterday in Appendix A. Let's literally zoom in. So let's trace. Choose graph trace, type a 2. Now, here's something interesting I found out. If you hit enter again after you type, if you type in a 2 and hit enter, and now hit enter again, look what happens. It sticks a point there that will stay there, which is kind of nice for what we're about to do next. So he went to trace, graph trace, typed a 2, hit enter a second time, and it locked a point there. Because now we're going to go to zoom in. So go back to window. Okay, go to zoom in, number 3. And it asks you for that center. And now you can put your center right over the 0.24. Because if we hadn't put that there, then it would have went away. Our trace would have went away. So you can put the center right over that and hit enter. And then put it over it again and hit enter. And let's keep doing it until we get a straight line. Straight, I said it again. A line, until it looks straight. That's what I meant to say. Okay, that looks pretty good. Now, you're all going to get different things because when you hit enter, you're going to be in a little different spot, so you're going to get a lot different decimal type things. Okay? Now, the idea behind this is we've now made that curve not curve anymore, or at least it doesn't look like it curves. So our tangent line, how many places does our tangent line touch this parabola? Just once, at the 0.24. If I was to draw a red tangent line on this, since I've zoomed in, the red tangent line would look like it lays right on top of the blue curve. But we know it would only touch in that one place. But if I found a couple of points on this blue curve, they'd be darn close to being points on the red line, right? Because they're so close together since I zoomed in. So what I want to do now is trace. So here's something else I've learned about trace. Go to menu and trace again. But this time, now don't hit graph trace yet. Go to menu and trace, and then go down here to trace step, number 3. Okay, and hit enter. Now, here when we trace, if we want to have control over how close we get to 2, here's where we would do this. Put in 0.01 and hit OK. Now type in a 2, hit enter. You gotta go back to window. You gotta go back to menu. You gotta go back to menu and trace and graph trace now. Okay, now hit the right arrow. And notice it goes 2.01 and hit it again. 2.02, and then you can hit the left arrow, and it goes 1.99 and so forth. Okay, and so now you could literally take those points and you could write them down. Okay, and do a slope calculation. All right, so we did it on the home calculator screen by doing the F1. That was easy. That saved us some work there. Okay, but they're also in some of the homework, they're going to say zoom graphically. Well, zoom graphically means they want you to zoom in on the graph till it's straight, and then they want you to trace in a couple points. They want you to write them down and do the slope calculation. So on our next quiz, there will literally be some questions where what I will be grading you on is go to 2.01 again. What's the y value at 2.01?
4.041.
And what's the y value at 1.99?
3.9601.
Okay, there will be some questions possibly on the next quiz where I will actually be grading you on seeing this work on your paper right here. Okay? Because the concept is so important that we understand that we're picking 2 points really close to 2 and we're doing a slope calculation. Also, the concept that's so hard or so important to understand is that those are 2 points on the curve, not on the tangent line. Okay? What we're trying to find is the slope of the tangent line, right? Because that's what the slope of a curve is. It's a slope at that 1 point. But we can't find slope with 1 point, so we're finding slope at 2 points on the curve, but they're darn close to points on the line, okay? It's just critical you get that concept through your head. So, we will have some of where we're doing this calculation. So back to the calculator. So then we would go, once you had done that, okay, go back to your calculator screen there now. Okay, and so then you would actually then just go in and type this in. And you don't have to, but you would just go ahead and type this in and it would come out 4 as well. Okay, but I want you to zoom in, and because I want to see these values, so I want to see that that you've done it. Okay, so the homework will have some of that. The homework will have some of the other that we did. All right, and turn to page 48, please, in your book. So, if I want to find, let's go back to the board here. If I want to find f prime of 2 for a function, now if I want to find the slope at 2, we got a couple of ways. Most of them are just estimates at this time. Okay, these are all just estimates of the slope of 2. One is sketch in a tangent line, do a slope triangle. Another one is pick 2 points really close together, either by zooming in graphically or just doing it on the calculator screen. Pick 2 points really close together, do a slope calculation. Okay. Sometimes, if you look at the middle of page 48, you just have a table as your function. Sometimes you don't even know what the equation is, but you just have a table of values. Well, in this example, they want to know the slope at negative 1.5. So if I had that table in front of me, what 2 points would I pick? Negative 1.6 and negative 1.4, right? Those would be the 2 values closest to negative 1.5. I would do a slope calculation with those. Now, I could do negative 1.4 and negative 1.5. I could do those 2. I don't have to pick one on either side. But in this case, it would probably be best. Probably be most accurate. So sometimes you just have a table of information. So zooming in means just pick the 2 points closest. Okay? All right, look over on page 49. They give you an example of absolute value. This is what I was talking about earlier. When you have a sharp point on the graph, there's no slope at that point. It's undefined. Zooming in shows it because all these curves, if we zoom in, think about it. If you zoom in on a curve, you can eventually make it look straight. But if you zoom in at the point of the V graph, it'll always look like a V. Forever and ever. No matter how many times you zoom in, you're still going to see a V. It does not straighten out. So there's no slope at that point. Okay? All right, go to page 50. Page 50 has a picture of the cube root graph. What would be the tangent line at the origin on the cube root graph? It'd be vertical, wouldn't it? And what's the slope of a vertical line? Undefined. So there's two main times when your slope is undefined. It's when you have a vertical tangent line. It'd be like that picture, or if you take the square root graph. The square root graph's top half of a parabola, right? Square root graph's top half of a parabola. Right there at the vertex, it would have a vertical tangent line. Okay? Those two times, and then at the sharp points on a graph, those are when the slope is undefined. Otherwise, if you got a curve, you can find the slope at any point. All right, that's pretty much it. So the homework will be a lot of that, doing slope calculations or sketching tangent lines and estimating rise and run. Okay, just getting across this idea of f prime as slope. So your homework, you can work on that for the last 20 minutes, is 1.5. If I didn't answer some of your questions on 1.4, and you want to ask me about those during these 20 minutes, please do so.
Right, probably. Let's take it slow. 300 questions, good test, and I'll do that.
Anna, I know you were working on those appendix problems way back then.
Yeah, I haven't done so.
At least those days are
But I still only like
doing nothing.
That's really good.
It's always in set.
You're overseeing
I'm not used to it. I'll go 11. Next to us back.
Don't you do that every time?
You should. I have noticed mine do that too.
Okay, so did you
Now,
want to
and then the others will go back to the same.
Probably.
Walk off the front and go back to settings, but then pick instead of giant, pick graphs and oh, whoops. Need to stop this.